Welcome to DAR Tutors. In this video, we will cover the fundamental concepts of equations, a key topic in IB mathematics. Applications and interpretation higher level. We will explore various types of equations, from power equations to quadratics, and learn how to solve them using a range of algebraic and technological methods. By the end of this session, you will be proficient in solving different forms of equations and analyzing the nature of their solutions. Our first topic is power equations. A power equation is any equation that can be written in the form x to the power of n equals k, where n is a non-zero exponent and k is a constant. The way we solve these depends critically on whether the power n is an even or an odd number. First, consider the case where n is an even integer, like in x squared equals 9. We need to remember that an even number raised to a positive or negative value yields a positive result. Therefore, if x to the n equals k and n is even, there will be two solutions. X equals the nth root of k, and x equals the negative nth root of k. This is often written as x equals plus or minus the nth root of k. If k is 0, x must be 0, giving one solution. And if k is negative, there are no real solutions, as an even power of a real number can never be negative. Now, let's look at the case where n is an odd integer, such as in x cubed equals 8. An odd number raised to a positive value is positive, and to a negative value is negative. This means there will always be exactly one real solution, regardless of the value of k. The solution is simply x equals the nth root of k. Let's apply these rules to solve some examples. Example 1. Solve x cubed equals negative 27. Here, the power n is 3, which is an odd number. As we've learned, an odd power equation will have one real solution. To find it, we take the cube root of both sides. The cube root of negative 27 is negative 3. So, x equals negative 3 is our solution. Example 2. Solve x to the power of 4 plus 5 equals 15. First, we need to isolate the x to the power of 4 term. Subtracting 5 from both sides gives us x to the power of 4 equals 10. The power n is 4, which is an even number. Since the right side, 10, is positive, we expect two real solutions. We take the fourth root of both sides, remembering to include both the positive and negative roots. The solutions are x equals the fourth root of 10 and x equals negative the fourth root of 10. This gives us x equals plus or minus the fourth root of 10. Example 3. Solve 5 minus 2x squared equals 11. Again, we first isolate the term with the variable. Subtracting 5 from both sides gives negative 2x squared equals 6. Then, dividing by negative 2, we find x squared equals negative 3. The power n is 2, which is even. However, the right side, negative 3, is a negative number. Since the square of any real number cannot be negative, there are no real solutions for this equation. These same principles apply to equations in the form x plus a, all to the power of n equals k. The key here is that we don't need to expand the expression. We can treat the entire bracket, x plus a, as a single variable. Let's look at an example. Solve the equation. Quantity x minus 3 squared equals 16. Here, the power is 2, which is an even number. The constant on the right, 16, is positive. This means we should expect two solutions. We start by taking the square root of both sides. Remember to include the plus or minus sign. So, x minus 3 equals plus or minus the square root of 16. The square root of 16 is 4. This gives us x minus 3 equals plus or minus 4. Now we have two separate linear equations to solve. First, x minus 3 equals positive 4, which gives x equals 7. Second, x minus 3 equals negative 4, which gives x equals negative 1. Therefore, the two solutions to the equation are 7 and negative 1. Now let's examine power equations where the exponent n is negative. These are often presented in the form x to the power of negative n equals k. To solve these, the first step is always to remove the negative exponent using the law of indices. The law states that x to the power of negative n is equivalent to 1 over x to the power of positive n. This means our equation x to the negative n equals k becomes 1 over x to the n equals k. From here, we can rearrange to get x to the n equals 1 over k and solve using the same methods we just discussed. Let's work through an example. X to the power of negative 5 equals negative 1/32. First, we rewrite the term with the negative exponent as 1 over x to the fifth equals negative 1/32. Next, we rearrange the equation to isolate x to the fifth, giving us x to the fifth equals negative 32. Now we have a standard power equation. The exponent n is 5, which is an odd number. Therefore, there will be one real solution. We find it by taking the fifth root of negative 32, which is negative 2. So our solution is x equals negative 2. Next, let's explore equations that are already in a factored form. An equation is in factored form when one side is completely factorized into a product of factors and the other side is 0. To solve equations in this form, we use a fundamental algebraic principle. This principle is called the null factor law. It states that if the product of two or more numbers is 0, then at least one of them must be 0. For instance, if the product of times b equals 0, it means either a is 0 or b is 0 or both. This law provides a straightforward method for finding the solutions or roots of a factored equation. We simply set each individual factor equal to 0 and solve the resulting simpler equations. Let's apply the null factor law with some examples. Example 1. Solve the equation quantity x minus 4 times quantity 3x plus 7 equals 0. This equation is already in factored form and equals 0. We can immediately apply the null factor law. We set each factor equal to 0. The first factor is x minus 4, so we write x minus 4 equals 0. Solving the first equation is simple. X equals 4. The second factor is 3x plus 7, so we write 3x plus 7 equals 0. For the second equation, we subtract 7 from both sides to get 3x equals negative 7, and then divide by 3 to get x equals negative 7/3. Therefore, the solutions are x equals 4 or x equals negative 7/3. It's important to remember that this method requires the equation to be fully factored and one side to be 0. If it's not, you must first rearrange and factor it. We now move on to quadratic equations, which are a major focus of the IB/AI/HL curriculum. A quadratic equation is an equation that can be written in the standard form ax squared plus bx plus c equals 0, where a, b, and c are constants, and a cannot be 0. A key characteristic of quadratic equations is that they can have 2, 1, or 0 real solutions. This is unlike linear equations, which typically have just one. We will explore several powerful methods for solving these equations. The choice of method often depends on the specific form of the equation and whether you need an exact or approximate answer. The methods we will cover are solving by factorization using the null factor law, solving by completing the square, using the quadratic formula, and finally, using technology like your graphics calculator. Our first algebraic method for quadratics is factorization. This method relies entirely on our null factor law. But first, we might need to do some rearrangement. There are 4 key steps. Step 1. If the equation isn't already in standard form, rearrange it so one side is 0. Step 2. Factorize the other side completely into its linear factors. Step 3. Apply the null factor law by setting each factor equal to 0. Step 4. Solve the resulting linear equations to find your solutions. Let's work through an example. Solve x squared equals 5x plus 6. Step 1 is to rearrange. Subtracting 5x and 6 from both sides gives us x squared minus 5x minus 6 equals 0. Now the equation is in standard form. Step 2 is to factorize. We need two numbers that multiply to negative 6 and add to negative 5. These numbers are negative 6 and positive 1. So we can factor the quadratic as quantity x minus 6 times quantity x plus 1 equals 0. Step 3 and 4 are to apply the null factor law and solve. We set each factor to 0. X minus 6 equals 0 gives x equals 6. And x plus 1 equals 0 gives x equals negative 1. Our solutions are x equals 6 or x equals negative 1. There are two important cautions to remember when solving equations. First, do not divide both sides of an equation by a variable expression. You could lose a valid solution. For example, consider x squared equals 5x. If you divide both sides by x, you get x equals 5. This is a solution. But by dividing by x, you've made an assumption that x is not 0, and therefore you lose the other solution, x equals 0. The correct way is to rearrange to x squared minus 5x equals 0. Factorize to x times quantity x minus 5 equals 0, and find both solutions. X equals 0 and x equals 5. Always rearrange and factor to be safe. Second, be very careful when taking square roots of both sides of an equation. For example, with quantity 2x minus 7 squared equals quantity x plus 1 squared. If you simply say 2x minus 7 equals x plus 1, you will only get one solution, x equals 8. You are missing another. The correct approach is to remember that if a squared equals b squared, then a must equal plus or minus b. This gives two cases to solve. A more reliable method is to rearrange to one side and factorize as a difference of squares. This gives you two distinct factors, ensuring you find both solutions, x equals 2 and x equals 8. Our second algebraic method is completing the square. As you would be aware, not all quadratics can be easily factorized. Completing the square provides a systematic way to solve any quadratic equation by transforming it into the solvable form. Quantity x minus h squared equals k. Here are the steps. First, ensure the coefficient a of x squared is 1. If not, divide the entire equation by a. Second, rearrange the equation so the constant term is on the right-hand side. Third, we complete the square on the left by adding quantity b over 2 squared to both sides. Fourth, factorize the left-hand side, which will now be a perfect square. Finally, take the square root of both sides, remembering the plus or minus sign, to solve for x. Let's apply this method to solve 2x squared minus 10x plus 3 equals 0. Step 1. The coefficient of x squared is 2, not 1. So we divide the entire equation by 2, giving us x squared minus 5x plus 3 halves equals 0. Step 2. Move the constant to the right side. Subtracting 3 halves from both sides gives x squared minus 5x equals negative 3 halves. Step 3. Complete the square. The coefficient of x is 5, so we add or 5 over 2 squared or f over 4 to both sides. This ensures the left side is a perfect square. Step 4. Factorize the LHS and simplify the RHS. The LHS becomes quantity x minus 5 halves squared. The RHS simplifies to 19 over 4. We now have our desired form. Step 5. Solve. Take the square root of both sides, remembering the plus or minus sign. We get x minus 5 halves equals plus or minus the square root of 19 over 4. This simplifies to plus or minus the square root of 19 all over 2. Finally, add 5 halves to both sides to isolate x, giving our exact solutions. X equals 5 plus or minus the square root of 19 all over 2. Our third method, and often the most convenient, is the quadratic formula. This formula is derived directly from completing the square on the general quadratic equation x squared plus bx plus c equals 0. Here is the formula. It's a fundamental result in algebra that provides a direct way to find the solutions to any quadratic equation. The solutions x are equal to negative b plus or minus the square root of quantity b squared minus 4ac, all divided by 2a. To use it, you simply need to identify the coefficients a, b, and c from your quadratic equation and substitute them into the formula. Let's solve the equation x squared minus 2x minus 6 equals 0. Here, the coefficient a is 1, b is negative 2, and c is negative 6. Substituting these values into the formula gives x equals negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times negative 6 all over 2 times 1. This simplifies to x equals 2 plus or minus the square root of 4 plus 4, which is 8, all over 2. To provide the exact solution, we should simplify the radical. The square root of 28 can be written as the square root of 4 times 7, which is 2 root 7. So our expression becomes 2 plus or minus 2. Root 7 all over 2. We can divide the numerator and denominator by 2 to get the final simplified exact solutions. X equals 1 plus or minus the square root of 7. We can gain powerful insight into the nature of the solutions to a quadratic equation without fully solving it. This is done by analyzing a special part of the quadratic formula. The quantity b squared minus 4ac, which is under the square root sign, is called the discriminant. It is represented by the Greek letter delta. The sign of the discriminant tells us how many real solutions the quadratic equation has. There are 3 cases to consider. First, if the discriminant is positive, the square root will be a real number. This means we will have both a plus and a minus term, leading to 2 distinct real roots. Second, if the discriminant is 0, the square root term vanishes, and we are left with only one solution. X equals negative b over 2a. We call this a repeated root. Third, if the discriminant is negative, the square root of a negative number is not a real number. In this case, there are no real roots. We can also note that if the coefficients a, b, c are rational and the discriminant is a perfect square, the equation has 2 distinct rational roots. Furthermore, if the discriminant is positive but not a perfect square, the roots will be irrational, like the root 7 in our previous example. This means they cannot be written as a simple fraction. Let's use the discriminant to determine the nature of roots without solving the equation. Consider the equation x squared minus 7x plus 9 equals 0. Here a equals 1, b equals negative 7, and c equals 9. The discriminant is b squared minus 4ac, which is negative 7 squared minus 4 times 1 times 9. This simplifies to 49 minus 36, which equals 13. The discriminant 13 is greater than 0, and it is not a perfect square. Therefore, this equation has 2 distinct irrational real roots. Now let's find the values of the constant m, for which the equation x squared minus 2x plus m equals 0 has a repeated root. Here a equals 1, b equals negative 2, and c equals m. For a repeated root, the discriminant must be 0. So we set b squared minus 4ac to 0. This gives us negative 2 squared minus 4 times 1 times m equals 0. Simplifying, we get 4 minus 4m equals 0. Solving for m, we find that m must be 1 for the equation to have a repeated root. We can extend this analysis to find values of m for 2 distinct real roots or no real roots. Using the same equation, x squared minus 2x plus m equals 0, we already found the discriminant is 4 minus 4 mia. For 2 distinct real roots, the discriminant must be positive. So we set 4 minus 4 miam to be greater than 0. Solving this inequality gives us m is less than 1. Any value of m less than 1 will result in 2 distinct real roots for the equation. For no real roots, the discriminant must be negative. So we set 4 minus 4 mem to be less than 0. Solving this inequality gives us m is greater than 1. Any value of m greater than 1 will result in no real roots for the equation. There is a very useful relationship between the coefficients of a quadratic equation and its roots. This topic is known as the sum and product of roots. If the roots of the quadratic equation x squared plus bx plus c equals 0 are alpha and beta, then their sum, alpha plus beta, is always equal to negative b over a, and their product, alpha times beta, is always equal to c over a. This relationship is a direct consequence of factorizing the quadratic in 2 ways and equating the results. It's a powerful tool because it allows you to find the sum and product of the roots without actually calculating the roots themselves. This is particularly useful when the roots are irrational or complex, or when you need to construct a new quadratic equation. By the way, if you're looking for more in-depth support with these topics or any other part of the IB Mathematics curriculum, DAR Tutors offers expert tuition. You can contact us for personalized online or home tuition in IB, A-Level, and IGCSE subjects. So, again, if the roots of x squared plus bx plus c equals 0 are alpha and beta, their sum is negative b over a, and their product is c over a. This will be a key skill for more advanced problems. Let's work through an example to see how this works. Consider the equation 25x squared minus 20x plus 1 equals 0. Find the sum and product of its roots, which we will call alpha and beta. First, we identify the coefficients. A equals 25, B equals negative 20, and C equals 1. Using our formulas, the sum of the roots, alpha plus beta, is negative b over a, which is negative 20 over 25. This simplifies to 20 over 25, or 4/5. The product of the roots, alpha times beta, is c over a, which is 1 over 25. So the sum is 4/5, and the product is 1/25. We can check this by finding the roots using the quadratic formula and adding and multiplying them. This confirms our results are correct. The power of this method is that we don't have to do that verification unless it is specifically asked. The sum and product of roots relationships are extremely useful for constructing new quadratic equations whose roots are related to the roots of a given equation. The general form of a quadratic equation can also be written in terms of its roots, alpha and beta. It is x squared minus the sum of the roots times x plus the product of the roots equals 0. Notice the minus sign for the sum of the roots. Any equation of this form will have roots alpha and beta. Let's work an example. The roots of the equation 4x squared plus 5x minus 1 equals 0 are alpha and beta. Find a quadratic equation with roots 3 alpha and 3 beta. First, we find the sum and product of the original roots, alpha and beta. For the original equation, a equals 4, b equals 5, and c equals negative 1. The sum, alpha plus beta, is negative 5 over 4. The product alpha beta is negative 1 over 4. Now we need the sum and product of our new roots, 3 alpha and 3 beta. The new sum is 3 alpha plus 3 beta, which we can factor as 3 times the quantity alpha plus beta. We know alpha plus beta is negative 5/4, so the new sum is 3 times negative 5/4, which is negative 15/4. The new product is 3 alpha times 3 beta, which is 9 alpha beta. We know alpha beta is negative 1/4, so the new product is 9 times negative 1/4, which is negative 9/4. Now we can construct the new equation using our formula x squared minus sum, x plus product equals 0. Substituting our new sum and product, we get x squared minus quantity negative 15/4 times x plus quantity negative 9/4 equals 0. This simplifies to x squared plus 15/4 x minus 9/4 equals 0. The simplest form without fractions is to multiply the entire equation by 4. This gives us our final answer. 4x squared plus 15x minus 9 equals 0. Any quadratic equation proportional to this one, for example 8x squared plus 30x minus 18 equals 0, will have the same roots. We now move on to the final two methods for solving equations. Using technology. Technology is a powerful tool in the IB/AIHL course, allowing us to solve equations that are difficult or impossible to solve by hand. A graphics calculator can be used in two main ways: with a built-in solver for polynomial equations, or by graphing both sides of the equation. The polynomial solver is typically found in the equation or program menu of your calculator. It allows you to input the coefficients of a polynomial equation, like a quadratic or cubic, and get the solutions directly. The graphical method works for any equation. You graph the expression on the left side of the equation as y1 and the expression on the right side as y2. The solutions to the equation are the x-coordinates of any points of intersection. If one side of the equation is 0, you simply graph the other side and find its x-intercepts, or roots. Let's see the polynomial solver in action with a cubic equation. We'll solve x cubed plus 4x squared equals 6 minus x. First, we must rearrange the equation into standard polynomial form with one side equal to 0. Adding x and subtracting 6 from both sides gives us x cubed plus 4x squared plus x minus 6 equals 0. Now we identify the coefficients for our cubic solver. The coefficient of x cubed a is 1. The coefficient of x squared b is 4. The coefficient of xc is 1. and the constant term d is -6. You would now enter these values into the cubic solver on your graphics calculator. The calculator will provide the solutions for x. The solutions are x equals 1, x equals -2, and x equals -3. The polynomial solver is extremely efficient for these types of problems, often finding exact solutions. Now let's see how to use the graphical method, which is versatile for solving more complex equations. We'll solve the equation 2 to the power of x equals x plus 3. This is a transcendental equation, which cannot be solved with algebraic methods. Graphing is our best approach. The first step is to define two functions in our calculator's y as editor. We define y1 as the left side, 2 to the power of x. We define y2 as the right side, x plus 3. Next, we view the graph. Adjust your window settings as needed to see all the points of intersection. The graph will show an exponential curve for y1 and a straight line for y2. From the graph, we can see 2 points where the functions intersect. These x values are the solutions to our equation. We use the calculator's intersect feature to find them precisely. After using the intersect tool for both points, the calculator provides the coordinates. The first intersection is at x approximately 2.86. The second intersection is at x approximately 2.44. These are the two approximate solutions to the equation. Now let's practice what we've learned with 5 IB-style practice questions. A full worked solution will follow each question. Pause the video and attempt each question yourself before watching the solution. This is the best way to master the material. Question 1. Solve for x 3 times the quantity x minus 2 all squared equals 6. Here's the solution to question 1. This is a power equation in the form x plus a yamen a k. The first step is to isolate the squared term by dividing both sides by 3. This gives us quantity x minus 2 squared equals 2. Now we have an even power, neplacht 2. We take the square root of both sides, remembering the plus or minus sign. So, x minus 2 equals plus or minus the square root of 2. Finally, we add 2 to both sides to solve for x, which gives us the two exact solutions. X equals 2 plus the square root of 2, or x equals 2 minus the square root of 2. Question 2. Given that the roots of the equation 2x squared plus kx plus 12 equals 0 are alpha and beta, where alpha is 3 times beta, find the possible values of the constant k. Here is the solution to question 2. This problem requires us to use the sum and product of roots. First, let's write down the relationships for the original equation. For this equation, a equals 2, b equals k, and c equals 12. The sum of the roots, alpha plus beta, is negative k over 2. The product of the roots, alpha beta, is 12 over 2, which simplifies to 6. We are given the condition that one root is 3 times the other, which means alpha equals 3 beta. We can substitute this into our equations. The sum becomes 3 beta plus beta, which is 4 beta, equals negative k over 2. The product becomes 3 beta times beta, which is 3 beta squared, equals 6. Now we have two equations and two variables, beta and k. We can solve for them. Let's use the product equation first. The product equation is 3 beta squared equals 6. Dividing by 3 gives beta squared equals 2. Taking the square root, we get two possible values for beta, plus root 2 and minus root 2. This means there are two possible cases to consider. In case 1, if beta is root 2, we substitute it into the sum equation. 4 times root 2 equals negative k over 2. Solving for k gives k equals negative 8 root 2. The roots would be root 2 and 3 root 2. In case 2, if beta is negative root 2, we find that k equals 8 root 2. The roots would be negative root 2 and negative 3 root 2. Therefore, the two possible values for the constant k are plus or minus 8 root 2. Question 3. Find the nature of the roots of the quadratic equation 4x squared minus 4x plus 1 equals 0 and verify your answer. Here is the solution to question 3. To find the nature of the roots without solving, we use the discriminant. First, identify the coefficients. A equals 4, B equals negative 4, and C equals 1. The discriminant is b squared minus 4ac. Substituting the values gives negative 4 squared minus 4 times 1. This simplifies to 16 minus 16, which equals 0. Since the discriminant is 0, the equation has one repeated real root. Now, let's verify this by solving the equation. Notice that the left side is a perfect square. It can be factored as quantity 2x minus 1 squared equals 0. Taking the square root of both sides gives 2x minus 1 equals 0. Solving for x, we get 2x equals 1, so x equals 1/2. As predicted by the discriminant, we have found one repeated real root. Question 4. Solve the equation x squared over 5 minus the square root of x plus 3 equals 0 using technology. Give your answer to 3 significant figures. Here is the solution to question 4. This equation is not a polynomial, so we will use the graphing method. We can rewrite the equation as x squared over 5 equals the square root of x plus 3. We will graph the left side as y1 and the right side as y2. We enter y1 equals x squared divided by 5, and y2 equals the square root of quantity x plus 3 into our calculator's graph editor. Graphing these two functions will show a parabola for y1 and a square root curve for y2. By using the calculator's intersect tool, we can find the coordinates of the intersection point. We find that x is approximately 4.2547. Rounding this to 3 significant figures, our solution is x equals 4.25. Question 5. One of the roots of the quadratic equation kx squared plus the quantity 1 minus 3k times x minus 6 equals 0 is the negative reciprocal of the other root. Find the value of k and the two roots.